So this is the nuclear decay series. It calls it a lab. Really, it's more of a worksheet, but we're going to treat it like a lab. And essentially what we do in this assignment is we are going to work out the decay series of a randomly generated unstable isotope. So you are going to have a unique unstable isotope that is unique to yourself. You're going to generate that using your T number. And it talks you through doing that here. So you're going to generate an isotope that is specific to you. And then there's a little overview here where it talks about how you will work out a possible decay series for your specific unstable isotope, with the ultimate goal of, I think, getting to lead-208. Yes, so that is our ultimate goal, is to get to lead-208. So your isotope is going to start out somewhere up here, and you're going to work out a decay series, and each of the isotopes in that decay series to get to that final stable isotope. So let's just talk through this real briefly here. So here at the beginning, we're generating our individual isotope, and let me just, can I write on this? I don't know if I can. I don't think I can. No, I don't think this is going to let me write on it. I wonder if I download it. No, I don't think I can write on PDFs. Okay. Well, let me just write on. I'll write off to the side here. I know I wish maybe I could do it this way. Let's see. If I make that just part of the screen. This should let me write on that. Ooh, why did that come up? That was weird. Okay. No, it's not letting me write there. Why is it not letting me write? I don't want to select objects. Well, maybe it won't let me write. Okay, well, we're just going to have to do this a different way here. So, apparently it's not going to let me write on that while this is still shown here. But anyway, I think it's not too complicated. Hopefully you can follow along with me just talking about it. So we have our T number here. So your T number is 8 digits long. So you're just going to write it in here. You'll have A, B, C, and D. So this is the first 2 digits of your T number, third and fourth, fifth and sixth, seventh and eighth. To get your individual isotope, you're going to take the average of your A and B. So whatever 2 numbers you have here, maybe you have 20 and 20 and 17 maybe. Take the average of those 2, multiply it by 0.1, and then add 90. And then it says truncate to the nearest whole number. All that's saying is that, you know, if the number you get is like 101.51, just take it to the nearest number. So that would be 102 would be your number at that point. So just whatever the closest whole number is, because we can only work with whole numbers. We can't have fractions of protons. So whatever the nearest whole number is, that is going to be your atomic number, which is the number of protons. To get the mass number, you're going to take C and D and get their average. So whatever your average is for these two values, multiply that by 0.3, and then add 230. So 230 is the smallest number, and really you can't even get 230. It's going to be at least slightly bigger than 230. So maybe you get 250 something. So kind of similar to what we did before, we're going to have to do a little bit of variations here depending on what number you get. So you're going to truncate to the nearest whole number, just like before. If the nearest whole number is odd, you're going to add 1. And then at that point, now that you have an even number, if the value is not divisible by 4, which should mean that it's divisible by 2, because if it's an even number, all even numbers are divisible by 2. But if it's not evenly divisible by 4, add 2. You need your number to be evenly divisible by 4. And I do say it has to be evenly divisible, which is to say that any number technically is divisible by 4. You can divide any number by 4, but you need a number that when you divide by 4 you get a whole number. So it has to be evenly divisible by 4. So if your number is not, add 2 so that it is. Okay, does that make sense? The process to get your individual unstable isotope. Are there any questions over that? Nope. Okay. The main things there are just make sure that your atomic number is a whole number. That one's kind of the easier one. And then your mass number has to be divisible, evenly divisible by 4. If it's not, you're not going to be able to get this to work correctly. And if you're thinking to yourself, wait a second, are you saying that every single unstable isotope out there is divisible by 4, its mass number? No. But every single isotope that will eventually decay to lead 208, or 280, oh sorry, it is 208, yeah. So every single isotope that eventually decays to lead 208 is divisible by 4. But not everything decays to 208. But that is our goal, is to get it to go to that weight. So let's go ahead and read through this real quick here. So you're going to walk through a nuclear decay series for a nuclide that decays sequentially all the way down to lead 208. The goal is to predict which radioisotopes should make an appearance and which types of radiation are emitted along the way, all the time staying as near the belt of stability as possible. The belt of stability, or valley of stability, is a collection of all the most stable nuclides. Most elements have multiple stable nuclides, and they are usually clustered together along a sort of path. The elements you'll be working with today have no stable nuclides. But they still have some nuclides that are most stable when they can attain. These most stable of the unstable nuclides are the ones you'll try to stay nearest. You are limited to 3 types of radiation for this exercise: alpha, beta, and positron. Consider how each type of decay affects the mass number and atomic number, and use that information to plan out your decay series. So each of these 3 kinds of radioactive decay that we can use have a specific, what it's called a chess move here. It's not necessarily a common term. Don't go to a different book and expect to find that somewhere. It's just in this particular lab, that's what they call it. So every time an alpha emission occurs, the atomic number and the mass number change in a very specific way. And they always change the same way. And the same thing goes for beta emission and positron emission. They always change the same way. So, and I'm not going to work through these for you here, just because this is part of the lab for you to work these out yourself. But just to give you kind of a hint or a clue here, think about what happens with alpha emission, for example. If you remember from the lectures, in alpha emission you lose 2 neutrons and you lose 2 protons. You lose 2 of both of those things. And so your isotope, which is indicated by the little X here, is going to move in a very specific way. It's going to lose 2 protons and 2 neutrons. And so the second X, showing where it shows up or where it ends up after the decay, will be in one of these squares here. And the kind of movement that happens, so for example, and this is not the correct answer, but just for the sake of example, if this box here is where it ends up with alpha emission, and again, it's not the correct answer, it's not actually where it ends up, but just for the sake of argument, the X goes from here to here. That will be true for every alpha emission. It would move down and to the right 1 spot. Again, it's not actually true, but if that was true, every alpha emission would give you the same result. You would move down and to the right 1 spot. And so you'll have a similar thing with beta emissions and positron emission. And by the way, the 212, 210, 208 here on the side, that is the same for these. It's just not carried over. Although, as you'll see, you won't necessarily actually need to worry about that for beta and positron emission, since if you remember correctly, the beta and positron emissions don't actually change the mass number. Okay, so our procedure here: use the table on the following page to map out your decay series. Begin by highlighting the boxes that are closest to the isotopes listed on the periodic table. These represent the belt of stability. And show the path you should endeavor to stay close, as close as possible. The decay series are known to have multiple branched paths, so don't despair if your decay series doesn't look exactly like the sample found online. Okay. So the whole table here goes from lead to, is that Einsteinium, I believe, is ES, is Einsteinium. So what this is asking you to do is to go to the periodic table and just look at the mass numbers on the periodic table. They should have very specific isotopes listed for everything from bismuth up. Lead technically has more than 1 stable isotope, if I remember correctly, but from bismuth upwards, everything either has only 1 stable isotope, which would be bismuth, and then all the rest of these have just 1 most stable isotope. So uranium, for example, is a 238. So let's see, 238, there it is, so 238, and uranium, so you would shade in this box right here, because that is the most stable isotope of uranium. And so you'll just do the same thing for all the rest of these. Find the most stable isotope of all of these elements, and just shade in that box. And let's see. And I don't really care like what color or anything you do, just as long as it's clear that you have the belt marked. So you might have to print this off and do it by hand and take pictures. If you can get this into a Word document, which I believe is possible to do if you download it and you can manipulate it in Word, you should be able to shade the boxes at that point. But it would probably be easier just to print it and then take a picture of it when you turn it in. So you should end up with kind of a down and to the right moving belt of stability here for the elements. Okay, so what you're going to turn in here, it says your chart. What you're going to turn in is your chart showing the plan for the decay series. The boxes that represent the belt of stability should be highlighted. Mark the boxes representing your stable nuclides. and mark each radioisotope that is produced during each step of your series, and then label the type of radiation emitted during each nuclear transition. And it says you can use a different color arrow if you like for each one, as long as it's clear what's happening. I don't really care the way that you represent it. And then you're going to give me the total number of alpha decays, beta decays, and positron emissions needed to get your stable isotope, or your unstable isotope, to become stable. All right. Questions about the worksheet? Any questions? No? No questions? All right. Well, I think I'll go ahead and stop the recording then, and we can move on here.